This lesson is part 2 of section 2.2 titled The Definition of the Derivative. Now today our objective is to discuss the relationship between differentiability and continuity of a function. Our second objective is then going to be to determine if a function is actually differentiable. So yesterday we worked on finding the derivative of a function, but what we're going to see today is that not every function is going to be differentiable at every value of x in its domain. So sometimes a function fails to be differentiable. So we begin our lesson by actually looking at the definition of the derivative. This is what we looked at yesterday in our previous lesson. So we say the derivative of a function f is another function we call f prime, whose value at x is given by the limit as h approaches 0 of the difference quotient here. Now, right next to this it says provided that the limit exists. So this last portion of the definition here is pretty important because what it says is that if the limit doesn't exist at that value of x, then your derivative fails to exist as well. So when you think about the way we prove that a limit exists, we have to prove that from the left and from the right that limit is the same. So we say then that in order for a derivative to exist, then the limit as h approaches a from the left, so here I'm using slightly different notation. Instead of the difference quotient, we're using f of x minus f of a over x minus a. It's just a different way of saying the same thing though as the difference quotient. So that limit as h approaches a from the left must be the same as the limit as h approaches a from the right. In other words, the right hand and left hand derivative must exist and they must be equal to one another. Now, today's lesson is all about trying to decide if a function is going to be differentiable at some value of x. Now, what we have to do first, though, is to make sure that our function f of x is continuous at that value that we're looking at. So, in other words, if x is equal to a, we have to make sure that our function f of x is continuous at a before we decide if it's differentiable. So, if that function is not continuous at x equals a, then for sure it's not differentiable at x equals a. But we have to be careful because sometimes even if your function is continuous at that value, your derivative can still fail to exist at that value. So f prime at a fails to exist even when a function can be continuous at that value. Okay, so to recap here, basically what we're saying is that if you want to figure out if a function is differentiable, you have to first check to see that that function is going to be continuous at that specific value you're looking at. So if it's not continuous, then it's definitely not differentiable. If it is continuous, you still have to check to make sure that the left hand and right hand derivative exist and are equal to each other in order to say that the derivative exists at that value of a. Okay, so what we're going to do is actually take a look at a function that is not differentiable at a point where the function is actually continuous. So we're going to look at the absolute value of x, and even though the absolute value of x is continuous at x equals 0, it actually fails to be differentiable at x equals 0. So we're going to show that it fails this definition here. Alright, so I actually lied. Instead of using that definition above, we're going to use the alternate definition of the derivative to show that the absolute value of x is not differentiable when x is equal to 0. So if we let f of x equal the absolute value of x and a equals 0, then when we plug that into that alternate form of the difference quotient here, we end up with this expression, the absolute value of x minus the absolute value of 0 divided by x minus 0. So if I simplify here, I get the absolute value of x over x. Alright, so now let's look at the limit as x approaches 0 from the left of the absolute value of x over x. Now, because we're coming in from the left, that means these values are going to be negative. So based off of the definition of absolute value, we have to take the opposite of x. Okay, so we're looking at, we're looking at the limit as x approaches 0 from the left of the opposite of x over x. Now, because these factor and cancel here, x over x becomes just -1, so I have the limit as x approaches 0 from the left of -1. Now, this sometimes gets a little confusing for students, but no matter what, if it doesn't matter what value you're approaching, if your function is a constant function, then your limit is just that constant. So we have the limit as x approaches 0 from the left, that's going to equal -1. Now, let's check the limit as x approaches from the right of 0. Now, as x approaches from the right of 0 here, since the absolute value says if it's positive, keep it the same, we just take the limit as x approaches 0 from the right of x over x. And in this case, these do cancel as well, and we're left with 1. All right, so your limit here as x approaches 0 from the right, that limit is equal to 1. All right, so what we're seeing here is that the limit from the left, sorry, I keep writing this over and over, but it's really important that you get the notation correctly. So the limit as x approaches 0 from the left, that is not equal to the limit as x approaches 0 from the right. Which means then that your function is not differentiable here at x equals 0 because f prime of x then fails to exist. Okay, it does not satisfy that definition above here. Okay, the limit has to exist, and in order for it to exist, the limit from the left and from the right must exist and be the same. Okay, and so here we say that f prime of x would fail to exist, and I should write at x equals 0. Okay, so in our previous example, what we were doing was showing using the actual formal definition of the derivative. We showed that our limit failed to exist, which meant that the derivative failed to exist as well. So that was a very formal procedure, all right? Now, if you have a graph of a function, you can actually spot when a function will fail to be differentiable as well. Okay, so looking at a graph is definitely an informal way of seeing when a function fails to be differentiable. So this is not a way to prove or justify that a function is not differentiable, but basically when you're looking at a graph, if the graph is not smooth and continuous, then the function won't be differentiable at that value. So first off, we have case 1, which shows a discontinuity. Okay. Now clearly, if a function is not continuous at a certain value, then it cannot be differentiable at that value. So here we see that you have a jump discontinuity at x equals 0, okay, which means that f prime of 0 fails to exist. Okay, I'm going to actually draw in the graph of each of the derivatives as well next to it, so leave some room here so that you can actually draw in a little sketch. But now let's talk about case 2. Okay, so in case 2 here, we have the graph of the absolute value of x. Now, I know we just showed formally above why this function here fails to be differentiable at x equals 0. So in other words, in this case, f prime of 0 also fails to exist here. Whoops, not fails, fails to exist. All right, so I know we did that with the formal definition above, but I also want you to tie it into a graphical reason why this fails to exist at x equals 0. So a derivative is simply the slope of a line that's tangent to the graph at some value of x. So if I'm looking at this value of x and I want to draw in a line that's tangent to the graph, it's going to fall right on top of it, right? And that's because the right-hand portion here is a linear function, and as we discussed in the previous lesson, you're going to get the same slope, okay? Now, if I pull that point even closer, I still have the exact same slope of 1, right? That slope here is 1. And as I pull that point closer and closer to 0, I still get a tangent that's going to be the slope of a tangent that's going to be 1, right? So the derivative here would be 1, which is what we saw above, right? The limit as x approached 0 from the right of that was equal to 1. So the limit of our derivative was equal to 1. Now from the left, if you do the same thing, you draw a line that's tangent here, you continue to draw in lines that have a slope of -1. So here you see visually, okay, these tangent lines don't approach the same slope. Okay, they don't have the same slope from both directions. So this is why we have, in this case, a corner. Okay, so if there is a sharp corner in the graph of a function, it cannot be differentiable at that value because the slopes approach two different values. Okay, so in case 3, we see another example of a function that's continuous when x is 0. So f of 0 is defined, right? It's equal to 0. But f prime of 0 does not exist. Okay, it also fails to exist. It's not differentiable here. Now the reason it's not differentiable is because, and again, you can relate it back to the slopes of tangent lines. So let me draw in some, I'll do the right-hand side in orange, okay? So we're approaching x from the right. All right, so we're approaching x equals 0 from the right. Now, if I draw a tangent line in here, this slope here is positive. So the derivative here is positive. Now, as I drag that point closer to 0, I'm not very good at drawing straight lines, which is sad. Okay, as I draw that line closer, as I move that point closer to 0, see how that slope is now becoming steeper? Okay, it's getting larger. It's still positive, but it's getting larger. And as I drag it even closer, okay, that tangent has an even steeper slope than this one. So let's say that slope was, I don't know, 2. Now this slope could be 4, but it just keeps getting larger, okay? So as I continue to drag that coordinate here, this point, closer to 0, eventually that slope, okay, is going to be so steep that we call that an undefined slope, all right? In other words, and I'm going to generalize the notation so it's not going to be x approaching 0. So the limit as x approaches a of your derivative, f prime of x, that's equal to positive infinity, okay? So from the right, your limit here was positive infinity. Now, if we do the same thing from the left, we draw in a bunch of slopes, we draw in a bunch of tangent lines and we examine the slopes. So here we start out far away from 0, and we draw that point closer. Sorry, these are bad lines. But hopefully you're seeing here that that slope is still positive, okay? All of the slopes here would be positive, but they are also going to be so steep that we would call them undefined. So the closer we get to 0, the more steep they get, okay? And then once we get so close to 0, we end up getting an undefined slope. So the limit as x approaches a from the left of your derivative here, that's also infinity. Now when that happens, that means you get a vertical tangent. So let me erase here. Okay, there is a vertical tangent at x equals 0. All right, so here's where I'm going to actually draw in the graph of your derivative function here. So f prime x is its own function, so we can graph this function as well. So what this is saying is that as x approaches 0 from the right, you end up going to positive infinity. Okay, so as x approaches 0 from the right, you end up going to positive infinity. In other words, there is a vertical asymptote here at x equals 0 on the graph of f prime of x. As you approach from the left, we have we're going to positive infinity. Okay, so this would be the graph of f prime of x. Based off of this graph here, we can determine that the graph of f prime of x would look like this. Okay, so to recap, you're going to have a vertical tangent on the graph of f of x at x equals 0. There will be a vertical tangent here because the slopes of those tangent lines, as you drew those closer and closer to x equals 0, those slopes approached positive infinity. Now, saying that your slopes start to approach positive infinity is like saying that your slope becomes undefined at x equals 0. That's why you do have that vertical line, right? This has an undefined slope. Now, the derivative function is the slope of a tangent line. So when the slope of the tangent line becomes undefined, that means the graph of your derivative function is also undefined at that same place. So that's why you have a vertical asymptote here at x equals 0. Your derivative function fails to exist at x equals 0 because it's undefined. The slope of that tangent is undefined. Okay, so that's the connection here. Hopefully that makes more sense now. Now, one last note before we move on to case 4. This little note here at the bottom is pretty important. It's how you show that there is a vertical tangent in the graph of f of x. It also indicates a vertical asymptote in the graph of f prime of x. So this is actually missing something though, because the limit of your derivative as x approaches from the left and from the right could also go towards negative infinity. So basically this is a case where the limit either heads to positive infinity from both sides or to negative infinity from both sides. Okay, so it could be plus or minus infinity. Okay, finally, case 4 is actually a subset of case 3. So there is a vertical tangent here as well in the graph. Here we see the graph of x to the 2/3 power. Now there is something called a cusp here at x equals 0. And like I said, there will be a vertical tangent here, but it's a different case than when you see just a regular vertical tangent. So the vertical tangent, those limits approach positive infinity or negative infinity together. Here, when we draw in our tangents, let me start here on the right-hand side. So as we approach here, we're heading towards positive infinity again, right? Those lines here get steeper and steeper until they start becoming undefined slopes. So from that side here, let me write it off to the side, the limit as x approaches 0 of the derivative, this is going to be equal to positive infinity on one side, okay? Now on the other side, let's draw these ones in orange. On the other side, as you can see, the slope here is negative, right? That tangent has a negative slope. It keeps getting steeper, but it's still negative, so we have a negative steep slope until finally that slope turns into an undefined slope as well. So the limit as x approaches, oh, I forgot to put to the right, sorry. So as the limit as x approaches 0 from the left this time, okay, that is equal to negative infinity. So here we're seeing two different directions, positive infinity and negative infinity. The slopes here were positive coming from the right, okay, but negative coming from the left. Now, in the graph of f prime of x, so let's draw this function in here. What this is indicating, again, is that there is another vertical asymptote at x equals 0 on the graph of your derivative function. And the reason is, again, because it's undefined. The tangent slope is undefined at x equals 0. But instead of approaching from both directions going positive infinity or negative infinity, now we go in opposite directions. So from the right, you're approaching positive infinity, and from the left, you're going to negative infinity. All right, to finish off, I just want to graph the derivative function now, right next to f of x here. So if we're going to graph this, we're looking at the slopes of the tangent lines. Now, if we drew a tangent here at that coordinate, then that has a slope of 1. And even if I pull it closer to 0, okay, that slope remains 1. So the limit here of that derivative from the right is going to be 1. So we're approaching 1 as we approach 0. All right, now from the left, we draw in, whoa, that's a pretty bad tangent. We draw in tangents and we look at the slopes, we examine these slopes. The slopes here are negative 1. And as we draw it closer to, we draw in that point closer to x equals 0, we stay with negative 1. We say that the limit from the left of the derivative is going to be negative 1. So the limit approaches negative 1 as x approaches 0. Okay, so here's positive 1, here's negative 1. So that's the graph here of your derivative function. All right, so to summarize the relationship between continuity and differentiability, I want you to think about the graphs that we just looked at. So a graph has to be smooth and continuous in order for it to be differentiable. So if it has a corner or a cusp or a vertical tangent, or if it's got a discontinuity, then it can't be differentiable. So basically, if you have a function that is differentiable at x equals a, then it had to have been continuous there as well. So in other words, differentiability implies continuity. It's also possible, though, that a function will be continuous at a and not be differentiable at x equals a. So in other words, continuity will not imply differentiability. So it doesn't have to be differentiable even though it is continuous at a specific value. All right, so let's try an actual practice problem here. So it says determine the nature of the graph of the function 1 plus x to the 2/3 near the point 0, 1. Okay, so first off, our function is continuous. And the reason why it's continuous, we need to show this. F of 0 is going to be equal to 1, right? If I just plug in 0 here into the function. And the limit as x approaches 0 of our function, that is also equal to 1, because I can just evaluate that by plugging it in here, and I don't get that indeterminate form. So these are equal, which means our function is continuous. Okay, so now that we know that it's continuous, let's decide whether or not it's differentiable at x equals 0. All right, so first let's find the derivative of f of x. So we've got f prime of x is equal to, now in this case the derivative of a constant is 0, so we'll just ignore that part. And x to the 2/3, that's a power function, so I'm going to multiply by 2/3 and then subtract 1 from that, so I get 2/3 times x to the negative 1/3. Now, something kind of significant happens here, because if you rewrite it like this, you can clearly see that x cannot equal 0. Right? X cannot equal 0, otherwise f prime of x is not defined. So that's telling you something about the graph of your derivative function here. So kind of foreshadowing here a little bit. Okay, so now let's investigate the limit here as x approaches 0 of our derivative. All right, so in order to investigate that, we need to check from both the left and from the right to see whether or not that limit does exist. So we've got f prime of x from the left, and the limit as x approaches 0 from the right. Okay, so f prime of x is 2 over 3x to the 1/3. Now, if we are approaching that from the left, like just analytically here, you're going to have a negative value inside there, right? And you're dividing 2, a constant, by a very, 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 very small negative number, which means it's going to go to negative infinity. So that blows up to negative infinity. Now the limit as x approaches from the right, this time when you look at 2 over 3 times x to the 1/3, this time that value is going to be positive, very, very small, but positive. So when you take 2 and divide it by a very small number, this also blows up to positive infinity here. So we're looking at the left hand and right hand side going to negative and positive infinity. Okay, so in the graph, as x approaches 0, we'll have a vertical tangent, or I'm sorry, a vertical asymptote on the graph of f of x, or f prime of x, sorry, and on the graph of f of x there would be a vertical tangent, okay? But they approach from two different sides. So we've got negative infinity from the left, positive infinity from the right, okay? So the graph of f of x has to have a cusp. It must have a cusp at x equals 0. So you're looking at a graph that looks like this. Oh, it's shifted up one. Let's redraw it in here like that. Okay. And you can see if you try to draw some tangent lines on here, the slopes on this side, they get steeper and steeper and they start approaching positive infinity, while on the other side here, those slopes, okay, they get steeper and steeper but negative, so they approach negative infinity. All right, so that concludes this problem. You're looking for the behavior, so there is a cusp on the graph of f of x, and on the graph of f prime of x, you see a vertical asymptote because of the vertical tangent that occurs on the graph of f of x. So there is a vertical tangent here as well, a cusp that occurs at x equals 0, and a vertical tangent on the graph of f of x. Okay, so throughout this lesson, we have been looking at the differentiability of a function at a particular value of x, so just a single value of x. Now we extend this concept to the differentiability on an interval. So we say that a function is differentiable on a closed interval from a to b if f is differentiable on the open interval from a to b and if the following limits exist. So both of these are simply one-sided limits, so you only have to show that the endpoints are differentiable. So basically, you've got some function here. Okay, here's a closed interval a f of a and b f of b. Okay, now as you approach a from the right here, and actually, whoops, that's supposed to be h approaching 0 from the right. So you're taking a point. This is a plus h comma f of a plus h. Okay, so as you take this point and you move it closer and closer to a comma f of a, that means h is approaching 0. All right, so we're approaching 0 from the right, meaning we're moving towards that endpoint from the right. Now, if that limit exists, okay, then it's differentiable at a f of a. And then you check on the other side if the limit here, as you approach b comma f of b, so as that point slides over closer, and now this point is defined differently as b plus h comma f of b plus h. But as you slide that point closer, you look to see if that limit does exist. Now, if both of these limits exist, then your function is differentiable on that specific closed interval. So this is actually supposed to be as h approaches 0 from the left. Sorry about the typos. Okay, now let's try to decide if root x is differentiable on this particular interval. So we're looking at a closed interval with a left endpoint at 0 and a right endpoint at x equals 4. So if we were to kind of draw like a little rough sketch of this, you've got one endpoint at 0, 0, because if you plug 0 into your function, you get 0. If you plug 4 into your function, you get 2. So these represent the two endpoints that we're looking at. Now we want to approach the left endpoint from the right. So we're looking to see if the limit as x approaches 0 from the right of our derivative here, if that exists. All right, so let's try to evaluate that. So first of all, we need to know what f prime of x is, so let's find that. So if f of x is equal to x to the 1/2, that means that f prime of x is going to be 1/2 times x to the negative 1/2. In other words, 1/2 over, 1 over 2 root x. Okay, so that's your derivative. Now, if we evaluate the limit as x approaches 0 from the right of 1 over 2 root x, then we're going to try to substitute in, let's think of a value that's really, really close to 0, but on the positive side here. So we have a positive value on the inside that's close to 0. We multiply it by 2. It's still close to 0. So this is going to be 1 over a value that's close to 0, okay, but positive. Now this is clearly going to blow up to positive infinity. So technically this limit does not exist, but we'll get to that in just a second. Let's finish off finding the limit of the other endpoint here. So we approach 4 from the left, and we'll end up with, after we just do a direct substitution in here, we end up with 1/4. So the limit as you approach x from the, as you approach your right endpoint from the left, that exists, it's 1/4, but your limit as you approach from the right of your left endpoint here, it does not exist, okay? So this means your function is not differentiable on 0 to 1, or sorry, to 4, okay? So it is not differentiable on the closed interval from 0 to 4. Now, if we're asking for the interval from 1 to 4, though, this time, since we've already done the work to check for the right endpoint, let's just do the left endpoint. We're checking the limit as x approaches 1 from the right of 1 over 2 root x. Here we do end up with a value 1/2. So this time, yes, it is differentiable on the interval from 1 to 4, and that's because your limit exists for your left endpoint, and it also exists for your right endpoint. So when we say that it goes to positive infinity, obviously that number isn't an actual limit because it just keeps getting bigger and bigger and bigger, so we say it does not exist. So if both endpoints don't work, it is not differentiable on that specific closed interval. All right, in our final portion of the lesson, this should go pretty quick here. We're going to take derivatives of derivatives. So there's a little bit of notation that you need to know. If you have a function f of x, then obviously the first derivative, we call that f prime x. But the second derivative, we take the derivative of the derivative, okay? And we call that f double prime. So here you can see some notation that means the same thing. So this is pretty common. We'll be using that a lot, and as well as this. These are called the differential operator. I haven't used that specific vocabulary with you, but that's the official name, the differential operator there. Okay, in the last few problems, I just wanted to switch up the notation just a little bit here. We have that differential operator once again, so we want to find the derivative of y with respect to x. So, oops, I guess I shouldn't label it as f prime x. Let's do it as the derivative of y with respect to x. That is going to be -6, because we're going to bring down that exponent here, times x to the -4th power. Now in B, they're asking us to find the derivative of the derivative, so this is like f double prime, okay? So if we want to find f double prime of x, then we take -4 and we multiply by -6 to get positive 24. Then we'll have x raised to the -5th power now. Now we're taking the derivative of the derivative of the derivative in C here, so this f triple prime here, we're going to multiply by -5, so we get -120, sorry, and then x to the -6th power. Okay, and then finally, I'd like you to try this one on your own. Basically here, whenever you see just a number here, they don't want to continue to write like a bunch of little, are these called apostrophes? Oh my god, my friend once called them flying commas. Anyway, the apostrophe gets kind of redundant here to keep writing them, so instead, as soon as you get past the third derivative, you start seeing an actual integer here. So I'd like you guys to go ahead and find that fourth derivative. All right, and that's the end of the lesson. Please make sure you do ask some questions on this. I know that differentiability is not an easy topic. There's a lot involved in finding the derivative function and also interpreting what the derivative function's graph would look like. So like I said, just make sure you ask some good questions and be productive in class tomorrow. Nice job. See you tomorrow.